So, hello, my name is Felix Büttner. I'm from the Helmholtz-Zentrum in Berlin in Germany, and it's my great pleasure to today talk about our latest experiment where we observe the laser-induced nucleation of skyrmions, and we find that they are unexpectedly nucleated on a picosecond timescale. So a magnetic skyrmion is depicted here for those of you who don't remember, and what we are looking at now are its transition from a uniform magnetic state depicted here to an array of these skyrmions depicted here. So we are looking at these transitions in the context of phase transitions, so where the order parameter is the topological charge of the system. Okay, so if we want to understand such phase transitions, we need to look at the energetics along the reaction coordinate. So what we are plotting here is the energy of the system of a single skyrmion as a function of skyrmion diameter. Now the equilibrium skyrmion parameters are defined by this energy minimum here. And in this diagram, the uniform magnetic state is here at the origin at 0, 0. So now you can already see that the skyrmion, in this particular example at least, is lower in energy than the ferromagnetic state. However, there is a strong energy barrier that one would need to overcome in order to go from such a state here, from a ferromagnetic state to a skyrmion state. And this energy barrier, which can exceed hundreds of thousands of kBt at room temperature, has topological origin. So this is a topological energy barrier which leads to this concept of topological protection. So because of this phenomena and this energy barrier, we expect actually the phase transition between these between a non-topological phase and a topological phase to be of first order. And there are numerous examples in the literature confirming this indication of a first order phase transition, including an Arrhenius decay of skyrmions after leaving the skyrmion stability phase pocket as reported by the group of Christian Bach. Then there is, if you go to the transition region, so the phase transition boundary between the uniform and the skyrmion phase, then the group of Wiesendanger in Hamburg has observed telegraph noise, which is indicative of a bistability between skyrmions and uniform state and a strong energy barrier between those two. And then in our own experiment, we have found that if we nucleate skyrmions by spin orbital current pulses, that the resulting skyrmion distribution is strongly localized at certain defect positions in the material. So this is really indicating that the process is extrinsically dominated. So like when you try to freeze water, the nucleation of the ice happens at defects in the water. And the same process is happening here. If we want to have a transition to a skyrmion phase, then this is very strongly driven by extrinsic defects. Now, given all of these insights from theory and from the experiments, we were very surprised in 2018 to see two papers coming up where they showed that with a single laser pulse you can actually nucleate a very large array of skyrmions. This laser pulse in this case has a femtosecond duration, so it's a very short pulse and producing a large number of skyrmions. So we first of all repeated this experiment in our own laboratory, and we found that this kind of process can not only be produced in chiral materials like platinum, coffee, BMGO, but also, very surprisingly, in achiral platinum, cobalt, platinum symmetric multilayers. So given these observations, we then started a systematic study to explore the phenomena of all-optical topological switching. So the first thing we started with is to investigate if the nucleated features, these round features, are actually skyrmions. For that, in platinum, coffee, BMGO, we injected current pulses and observed the skyrmion trajectory. And the skyrmion trajectory we found is inclined with an angle with respect to the current direction. And this angle here is characteristic of the skyrmion Hall effect, which is directly showing the topological properties of the skyrmion. So it's deflected because of the topological charge. This is less surprising than the result in platinum cobalt platinum, where we performed Lorentz transmission electron microscopy to observe the chirality, the local chirality in the system. And what we find is that all these little features, these little circular features here, are either uniformly black or uniformly white, meaning that they are either completely clockwise or completely counterclockwise in chirality. So there's no defects in the domain 1, because there's no defects means that they are skyrmions. There is no chiral symmetry breaking, so that's why we have black and white skyrmions, but all of them are skyrmions. So 100% of these textures are skyrmions after laser nucleation. So next we went to study the fluence dependence of the process. And what we actually find is that above a certain very sharp fluence threshold, we see that only a single laser pulse transforms any initial state, a stripe domain state or a uniformly saturated state, into a skyrmion array. Whereas below that threshold, tens of thousands or even millions of pulses are required to perform this transition. So below there might be an Arrhenius activation, but above this threshold, this is not an Arrhenius type of transition. It's rather an indication of a phase transition signature. So next, we studied the distribution of skyrmions. So this is now looking at a nominally same material, both platinum, coffee B, and MgO, grown in the same chamber. Now, after laser nucleation and after spin-orbital nucleation, you clearly can see that after spin-orbital nucleation, you see this inhomogeneity of the distribution, whereas in the laser nucleated case, skyrmions were very homogeneously distributed, so the remaining variance in this case is only due to shot noise. So this is really showing us that this laser-induced skyrmion nucleation is an intrinsic mechanism that does not rely on defects in the material. So really, to understand the process and the time scale and what's happening here dynamically, we went to the European X-ray for electron laser and we performed a study in temporal and reciprocal space. So what we did here is to record small angle X-ray scattering images, which are representing the Fourier transform of the magnetic state of our system, with 3 X-ray pulses and one infrared laser pulse. So one X-ray pulse is before the laser, one is shortly after the laser, and one is long after the laser pulse. So these first and third pulses are control experiments. What we see is that we start always with an initially saturated state, and we end up in a skyrmion state. So this pattern here is what we confirm also by static imaging is a skyrmion state. Now, transiently, interestingly, we find that there is a distribution of scattering across the entire detector and almost no concentration to a specific Q range. So this is showing that all length scales are present transiently in the system, and this is what we interpret as a transient fluctuation state. Now, to really understand the nature of the state and what is happening and why it leads to the formation of skyrmions, we collaborated with colleagues in Mainz who performed atomistic simulations. And what they see is, first of all, statically, that there is a short-range ordered phase of skyrmions just below the paramagnetic state, which can be reached from the ferromagnetic state at low temperatures. So just by cycling the temperature, you can go from the ferromagnetic state to the skyrmion state and back. And the very surprising fact here is that if you do this atomistic spin dynamic simulation, that if you heat into this intermediate skyrmion state, then you immediately get topological switching and building of a net topological charge. So this is immediately happening, meaning that it's not a first order phase transition. So why is this happening so quickly? And also let me note that after going back to the original low temperature state, these skyrmions remain stable, so as in the experiment. So what is happening here is that we have a transient lifting of the topological energy barrier. So the topological energy barrier is proportional to the topological charge, the exchange energy, and the thickness of the magnetic field. So transiently, we have a decoupling of our layers. So we have a stack of 15 layers, And transiently, these are decoupled. So instead of having 15 times the cobalt thickness, we have only 1 times the cobalt thickness of each layer. And that is reducing the factor T to 1/15. Then we are also very close to the Curie temperature, where the exchange energy is then largely reduced. So both of these factors are largely reduced, so the energy barrier is de facto eliminated, meaning that there is a direct path now from the initially saturated state to the skyrmion state here. So because of this elimination of topological energy barrier, skyrmions can nucleate very rapidly. So this is our understanding now. Why do we trust these simulations? Because they agree with the experiment in 4 key areas. The first one is if we plot the scattered intensity distribution here in the experiment. So this is the scattered intensity as a function of time delay. We see a certain characteristic pattern. And now in the simulations we can perform the same, we can reconstruct the same pattern by just Fourier transforming the simulated magnetization maps, and we see that we qualitatively reproduce the same result, even though the time scale is different here, which is just due to simplifications of our model that we had to apply to make it computationally feasible. Moreover, we get 100% skyrmions in their final state, both in the experiment and in the simulation. There is a sharp fluence threshold for the process, so in the simulations we need to reach that fluctuation state. We need to reach that intermediate skyrmion phase. And both of them are intrinsic mechanisms, so there is no defect, there's no defects in the simulation, and there's evidently no defects needed in the experiment. Now, finally, if we want to understand the time scale, how fast is this switching happening, we look at the total intensity as a function of time, again in the experiment, so this is what we deduced from the experiment, and what we find that after 300 picoseconds, we get a saturation of the total intensity almost to the final state intensity drawn in orange here. So now we need to understand that we have this multi-layer, so if we probe scattering, we get only large scattering if all these layers have the same magnetization. So evidently at 300 picosecond there is fully this coupling between the layers is fully restored. So the effective the film thickness is again the full thickness of the magnetic material, and so the energy barrier is restored. So there's no topological switching after 300 picoseconds. So as a summary, I hope I convinced you that we would expect the skyrmion phase transition to be of first order with a very large topological energy barrier, and we expect it to be rare, slow, and defect-driven. However, in case of all optical topological switching, very surprisingly, we find that this process is very fast, completes on a timescale of 300 picoseconds or faster, and it is mediated by a transient topological fluctuation state, which is eliminating the topological energy barrier. Now what comes next? Evidently, we want to follow this process in real space. We have so far followed it in reciprocal space. We want to see, like in real space, when topological textures arise, and it would be also very nice in this context if we could measure topological charge directly as a function of time. So with this, I would like to emphasize that this has been a very collaborative work. Many people have been involved from the Massachusetts Institute of Technology, from the Max Born Institute in Berlin and the TU Berlin, but also a lot of people at the instruments like the European XFEL, at the SCS beamline, the detector development team at the European XFEL. The TEM imaging has been performed by Klaus Ropers in Göttingen, and there has been extensive theory support from Bertrand Dupé and Marie Böttcher at Sinova in Mainz, and from Johan Menting in Nijmegen. Okay, with that, thank you very much for your attention, and I look forward to our discussion at the interview.